So you've probably played around with ChatGPT. Maybe you've used Dolly or Midjourney. But have you ever stopped to think about what the T in GPT actually stands for? Because, it's the key. It is the core technology behind this entire AI revolution. Okay, let's dive in and really figure out what a transformer is. So GPT stands for Generative Pre-trained Transformer. Now, generative and pre-trained, they kind of make sense, right? It generates things, and it was trained beforehand. But that last word, transformer, that is the secret sauce. It's this specific type of neural network that is the engine behind pretty much all of the incredible AI tools we're seeing pop up everywhere.
So that's the big question, isn't it? What is a transformer actually doing under the hood? I mean, how does it really work? Well, to get a handle on how a transformer works, we first have to understand the surprisingly simple game that all of these huge AI models are playing. It's basically an engine for generation that's built on one single core idea: prediction. That's right. I mean, beneath all of that mind-bending complexity, a large language model is just a super, hyper-advanced next word, or to be more precise, next token prediction machine. Its entire job is to look at a chunk of text and just guess what comes next. That's it.
So you might be wondering, okay, how do you get from just predicting one word to writing an entire essay? Well, you use this incredibly simple loop. The model makes a prediction, it picks a word from that prediction, it tacks it onto the end of the text, and then it feeds that whole new longer sentence right back into itself to do it all over again, and again, and again. And it turns out the sheer scale of the model makes all the difference in the world. It's like night and day. An older, smaller model like GPT-2, well, it just produces nonsense. It's gibberish. But a much, much larger model like GPT-3 can use that same simple loop to generate a story that's not only coherent, but actually seems to understand the context of your prompt. Okay, so the model predicts the next token. But wait a minute. How does a computer, which only gets numbers, actually work with words and language? Well, the first crucial step is to translate our words into the language of math. You have to turn them into coordinates. So the whole process kicks off by breaking your text, your prompt, into these little chunks called tokens. Now, these can be whole words, sure, but they can also be parts of words or even just a piece of punctuation. They are the absolute fundamental building blocks that the model is going to work with. Then, each one of those tokens gets converted into a very long list of numbers. This is called a vector or an embedding. And honestly, the best way to think about this is that each vector is a set of coordinates, which places the words somewhere in this vast, high-dimensional meaning space. And this right here, this is the classic example that just beautifully illustrates how this whole space works. The directions in this space actually have semantic meaning. If you take the vector for the word king and you literally subtract the vector for man, and then you add the vector for woman, you land almost exactly on top of the vector for queen. It's like relationship algebra. It's incredible. And just how high-dimensional are we talking here? Well, for GPT-3, every single one of those token vectors has, get this, 12,288 dimensions. That is a ton of room to capture all the subtle nuances of human language. All right, so we've successfully turned our words into these massive, high-dimensional vectors. Now, let's actually follow one of these vectors on its journey as it travels right through the heart of the transformer network itself. Here's the basic roadmap. A vector starts out as a simple word embedding, right? It then gets passed through two different kinds of processing blocks, an attention block and then a feed-forward block, over and over and over again. And with each pass, it's just soaking up more and more context from all the words around it. So what are these blocks actually doing? Well, the attention block. That's the revolutionary part. You can think of it as the place where every word vector gets to look at every other word vector in the sentence and basically ask, hey, how relevant are you to me? They exchange information and build this map of relationships to figure out which words are the most important for understanding the context. Then, in the feed-forward block, each vector is processed on its own, in parallel, as if the model is kind of taking a moment to think about everything it just learned before the next round of attention. Now, here's a really, really important thing to get straight. You have to distinguish between the model's weights, which are like its permanent brains learned from trillions of words during its training, and the input data, which is just your prompt that's flowing through the network for one single run. The weights are the permanent roadmap that tell the data where to go. Okay, so after all that processing, all that talking to each other, all that soaking up of context, The network now needs to turn its final context-rich vectors back into an actual prediction for the next word. It has to turn math back into language. And to do this, the model looks only at the very last vector in the whole sequence. Yeah, that's it. By this point, that single vector has absorbed all the relevant information from your entire prompt, and it's ready to make a really well-informed guess about what should come next. So that final vector is used to generate a raw score for every single possible next token in the model's vocabulary. But raw scores aren't super useful, so to turn them into something we can work with, a function called softmax comes in and converts them into a nice, clean probability distribution, where every value is between 0 and 1, and they all neatly add up to 100%. And this is where things get fun, because we can actually get in there and play around a bit. By adjusting a setting called temperature, it's like we're turning a creative dial. A low temperature makes the model really predictable and safe. It'll always just pick the most probable word. But if you crank up the temperature, you encourage randomness and creativity by giving some of the less likely words a real chance to be chosen. And just to put all of this into perspective, remember those first and last steps we talked about? Turning words into vectors and then turning vectors back into word predictions? Well, those two steps alone account for over 1 billion of GPT-3's parameters. And that's just a tiny fraction of the staggering 175 billion parameters in the entire model. The scale is just mind-boggling. So we've seen the whole journey, right? Words become vectors, vectors flow through the network, and a final prediction is made. But that central step, that moment where vectors look at each other and decide which connections truly matter, that is the whole game. The ability for a word at the very beginning of a long paragraph to directly connect to a word at the very end. That was the breakthrough. This powerful context-building mechanism is called attention. And it's not just part of the transformer. It is the reason the transformer changed everything.